Hello and welcome back to the channel. It's Mark from Powersonic and Apprentice 121. Today we are looking at a water leak damaged property. So this is a massive leak from a water cylinder up in the loft space. I'm going to take you through the whole thing. We've got to do an Eicr and decide if this is safe or not. I'm going to spin you around and show you exactly what we've got to start with. So I'll open the zoom right out. You'll see the ceiling's been dropped in the kitchen. There is parts of this property I can't show you because it's got the occupiers stuff still in, and I don't want to show any of that on camera as always. But you'll see we've got an issue with some of these spotlight terminations straight away, and there is some other kitchen fitter magic gone on in here, which we will speak about. Obviously that's not part of the flood. You can see there has been some leaking going on under the bathroom, which is up here. That's not the cause of the main problem that we're investigating. We'll start at the beginning. This is the current consumer unit. See, it's a 16th edition board, so we do have an RCD on there for the socket circuits. The lighting circuits, not so much. The lights have actually stopped working on this one, and we'll explain why as we move through our inspection. But we're just going to run through it all visually together, and then we're going to break some of the testing down, and I'll show you little bits of that as well. So we'll start off outside. Okay, so outside we've got the meter box, and you will see we've got a nice main isolator. I'm going to get that locked off so we can work quite safely. 80 amp fuse coming in. We've got our earthing conductor as well, so we can do a few little tests out here. Make sure we've got any leakage currents floating around the earthing system because it is a PME. And yeah, get this locked off, and then we know we're perfectly safe inside, and we'll carry on with the video. I will show you the source of the leak next. That's a good one to begin with. I'll just pop my little light on here. Let's ramp it right up. So the actual leak itself, if we spin around into this room, you can see we've got another ceiling down. These had all been disconnected, so they're not energised. When I first inspected this, obviously the ceiling was up, but there are a few issues with the wiring. It's nice that the ceiling's down because you can kind of see exactly what's what without having to go into the loft space. It is only this side of the property where the ceiling's out, but looking at it, the original install seems to have been done fairly well. You can often get a good feel of it just from looking at the clipping of the cables, the way they're dressed in, the accessories. You know, it's always a nice way of judging what the wider install's like. Now I don't know if you can spot just up there, but that's where the tank was. So it's a big cold water storage tank. And then obviously in this cupboard here was hot water tank. Now that had been leaking unnoticed for days. So it flooded all of this. All these carpets were just, it was like a swamp. It's really bad. And obviously when that's come up, we can see here there's a junction box under there. So we're going to have a look in that. I think that is for all of the downstairs lighting. They've brought it all back to one central point, and I'll show you why I think that when we go downstairs. We've got little en-suites and such. Yeah, so we've had a lot of water ingress to electrical accessories. It's kind of flooded all the way through these walls. These were all soaked. It's got in all of the sockets as well. The light bulbs themselves were full of water, so it's obviously been leaking into all of those. And they're actually sizzling away. The lights hadn't tripped, they just weren't working because there's lots of sizzling and arcing going on. Yeah. And out into the hall, this was all soaked. This side of the property seemed to bear okay, so we're not going to look into that one with you guys on camera. Obviously I will be testing that. It's just got bits and pieces of the customer's possessions in. And then this side of the front room again, the water had dripped all down these walls into the sockets. These were all soaked. We've had the drying out report. You can see some of the signs where it's dripped away down the walls. So it's fully dry now. The company who came in and stripped out, you can see the evidence of it down the wall here as well. I've passed it off as dried out now, so we can do a proper Eicr on it and be sure in what we're doing. And the reason I said about that junction box is if you see there's all those cables going in together. You can also see here, this must be the supplementary bonding that you can see running across. It comes across this way and then pops up into the bathroom. So you can visually identify that is running all around the bathroom from point to point, and then back to the consumer unit as well. It's a nice way of being able to verify that one. Yeah, so we can have a good look through. One of the interesting ones actually, which I'll show you, and it's nothing again to do with the flooding as such, but there's this kitchen fitter special here. I'm really not a fan of this, where twin and earth cabling is laid underneath the cabinets or even clipped behind them on the wall. Reason being, if you get any kind of rodents running around under here, the first thing they're going to do is start nibbling on that after they've had a bit of the leftover scraps behind the kickboards. So it's not something that I think we should be doing. They want to be in containment at the very least, or plastered into the walls. That way, you know, it's not a possibility. And here is, when I first came to do the inspection to get them some power on so they could get the drying out equipment in, dehumidifiers and such, there was actually a fault on the kitchen socket ring final, and it was due to Mr. Rat having a good nibble. He'd gone through the ring final circuit, spin you around, under here. So we managed to find it easily enough, which was lucky. It was on the floor rather than behind the cabinet. But yeah, to keep in mind, if you are wanting to make things easier, supposedly for the next people who come along to fit a kitchen in 20 years, just remember that that brand new 30 to 50 grand kitchen that some people have thrown in might need to come back out if you've popped some clip direct cables behind the units. I think that's something that you'd be well worth avoiding. That's just my opinion. I'm going to get set up now near this consumer unit. We're going to run through some of the tests. Obviously we need to go around and open up these junction boxes. I'll see if I can find any more of them as well around the place. We'll have a good look around the loft, and then it's just a case of trying to get some test readings for the final circuits, live and dead tests. I'll pop in little clips of bits and pieces of both as we move along. So obviously I've shown testing videos on my channel historically. I think there was one doing some live testing at a rental property not too long ago, and I demonstrated some ZS testing. I think I didn't get the full range of dead to live testing in my office unit actually not so long ago. So there are some videos on the whole thing if you want to go and check that out, but we'll maybe do an IR test on one circuit and continuity test on another, and then maybe get some live ZS measurement on a socket or a light fitting or something, and clip it all together in this video so you can see, and then I'll run around at the end with the conclusions of the findings, and we'll see what we think together. So I'll catch up with you in a little bit. So this is the little junction box that we've got here upstairs. You'll see it's been done in old chalk block, but again, nice and tidy. I like how the cables are all labelled. That's always very helpful. You see that's the kitchen just below us there. So yeah, that's another point that we can do some testing from as well and see exactly what we've got. If we do have any issues with the IR values, especially being able to break the circuit down from somewhere like this, very useful. Yeah, so that's a nice find. And again, if you're doing your EICRs on something like this, we need to be opening up every accessory, inspecting every termination, any junction boxes that you can reasonably get to without taking apart the entire building. You need to be doing that. This is one where there's obviously been a lot of water make its way into the electrical system, and we've got to be absolutely certain that it's safe. And one of the recommendations I'll be making regardless is that all of the accessories are swapped. So even if we find out that the cabling is okay and that it's actually not really suffered that much damage through the course of the leak, you know that the accessories at the very minimum are all changed. And it's very, very likely that a bit of rewiring is going to be needed for some of the cables where we've had consistent water flow running through them, because you've got all of that arcing that's potentially making its way back up through the conductors and damaging some of the insulation. I'm sure we'll see that in some of the test results we're going to get. So yeah, that's where we're at. I'm going to jump on with this now. I just thought I'd show you that little junction box. If I find anything else, I'll pop it in along the way as well on the inspections. Otherwise, there's very little point me showing you opening up socket fronts and light switches. If I find that they're in order, there's nothing to report really, and I think that's going to be the case having looked at this. The original install seems to be decent, and there's not really been an awful lot done with it from the point it was first all put together. So aside from that kitchen fitter magic that I showed you before, I think we're going to be in reasonably good order in terms of the original install. If I do find anything where we've had some of the water damage causing an issue, I will of course show you it. Otherwise, we'll cut straight to the testing at the board. Okay, so rather interestingly, we've got around 60 odd milliamps of leakage current floating around there on the earthing system. Obviously my install's off, so that's coming from somewhere else. It can't possibly come in on this installation, and that's on the AC scale. And obviously if I move that over onto DC as well, you see there's a little bit of DC leakage current. With this it does work better if you are between the line and the neutrals together. Obviously I don't have access to them while the system here is switched off, so we can only take that measurement through the earthing conductor. And this is the TIS 570 clamp meter. It's absolutely brilliant actually, this one. You can see it bouncing around there. So there's obviously something going on in a neighbouring property. Look at it there, just bouncing up. So I might leave that sat on there and we'll set it to do its max and minimums. So we'll leave it set and see what maximum value it comes up with while it's just on the CPC, well, main air to the property there. See what it comes back with. Okay, so this is the live test now for getting our ZE and our PFC. It's important now, we know that this is energised, that you've got some PPE on. I've got the arc flash shield on and my road gloves. Also the GS38 probe on the end. I have got some of the long probe extenders, but I prefer to use this one because it's got a little button on it so I can start the test. Essentially you've got your earth disconnected. We don't want any of the parallel paths in place while we take this measurement. And I'm now going to probe onto the incoming line and see what value we get. So if I pop my probe on, the test set should start to measure voltage, which it is doing. I hit the go button on the probe and you can see I'm off there now. It's measured 0.17 and just over a kiloamp on the PFC as well. And obviously we now need to repeat that test between the line and neutral. So I'm going to go and get the long probe extenders on now. We'll do that on the main switch and see what value we get there as well. So with this you'll see I've connected the main earth back up. When we're getting a measurement for your prospective fault current, prospective short circuit current, it needs to be with all the bonds and earths connected. So you're going to measure that highest value of current that could flow under fault conditions within an installation. So we want to be on the loop impedance, make sure we're between line and neutral, we've got the probes connected in. Now with this I'm using the long reach probes, just to try and keep myself at an extra specially safe distance. So with these two extended probes we're going to make sure we're on the terminals. I'm not going to hang about here because obviously I'm inside a live enclosure. And I'm happy with that. So we've measured 1.28 kA on the prospective fault current there. The actual Z value is very similar, so that's the impedance between the line and neutral. We are getting a little bit higher on the prospective fault current, that's because the bonds are connected basically. But yeah, I can now put this back together and carry on with some of the testing. Make sure we've got a good isolation in place. So I brought you in a little bit closer here because obviously we've made the isolation outside, that's now all locked off. Got my voltage indicators, we've got the board up here. I'm not going to run through the whole safe isolation procedure. There are the stepped guides from the ECA which I'd recommend you going and taking a look at. Basically this is the kind of training you need to get from somebody on a one-to-one basis, so a mentor or somebody at college. There's so many different ways to go through ensuring you are safe while you work. I wouldn't want someone to watch one of my videos and then think that's how I need to do it. I have shared little guides in the past. I won't be doing that kind of thing anymore. I just don't think that's a sensible thing to do. But in essence, you need to prove that your tool works. So you've got your proving unit there. Get the tool in and make sure your voltage indicators are actually working, and then make sure you measure between your lines and your neutrals, your lines and your earths, and then make sure that your voltage indicator is working at the end of all of that as well, and then you know you're perfectly safe with inside this board. The other reason I'm not doing it is the way I've had to mount the camera up, and you'll see this when we're watching the rest of the video. This is a really small space, so there's next to no room. I'm literally holding my phone in one hand and I've got these in the other. It's just a bit of a faff and a nightmare, and I don't want to fudge it and then have people thinking that's how you do it when I've not done it right. So yeah, we'll leave that with that. I'll just pop you down on top of the bag I've got set up. You can see my little stand there, very professional. So that's my little tripod I'm going to have you guys set up on now while you watch me working through doing some tests on this board. Okay, so we know with reasonable confidence that this installation is now off and isolated. The main switch outside is locked off. I've seen functionally it doesn't operate, none of the sockets have power to them, nothing's currently on, the lighting's not working and such. But if you're going inside an enclosure before you've verified that it's dead and safe to work, you should always assume that it could be live and take appropriate measures with your PPE just to cover in that case. And yeah, this would be considered by some as being over the top. Got the big rubber inners on, I've not put the outer leathers on in this case. And I've got my arc fault flash base guard, just a few of the basics to make sure that you are keeping yourself as safe as possible. If you're inside a known live enclosure, obviously you need to do an arc flash survey, and that's a whole new thing that lots of people are getting to grips with at the minute. It's good to see that being spoken about across social media. But as I say, I'm reasonably happy that this is actually dead. I'm just going through the process of verifying it. And while I do that, putting a bit of extra PPE on just in case it is no hardship. You know, it's seconds to stick a helmet on and throw a pair of gloves on. So as I said, I didn't want to show that process in full. You'll have seen me just very quickly fast forward that through. I now know that that is dead, so there's no electrical energy in there. I can happily carry out the rest of my testing, knowing I've got that lock on the isolation point outside. There's no prospect of any electrical energy getting introduced into this system while I'm running through any of my dead tests. I can take my PPE off and just wear what's comfortable. Again, basics. So just make sure you're keeping yourself safe as best you can at all times. At the very least, you want your proving unit and your GS38 guards on, which this has anyway. And yeah, bit of extra PPE never hurt anyone, did it, at the end of the day. So I'll move on with this testing process now, and we'll see what kind of numbers this is going to chuck out at us. Yeah, let's get on with it. So obviously with this, there's a process to run through where you go through the dead and then the live tests. I already have a value of ZE and PFC. I haven't shown that on camera, but I'll maybe chuck it in again a bit later on. I'm going to basically work through the socket vinyl circuits now, just get my end-to-end resistances and then all of the crossover values. We can do some insulation resistance testing because everything is now disconnected and unplugged. Then likewise with the lights, we've got our continuity of the CPCs and making sure we've got our R1, R2 measurements. Then we can do some insulation resistance testing. Obviously there are some lighting accessories still connected in circuits, so spotlights and such. So that will be with your line and neutrals together to earth. And I think there's some clarification coming on that in Amendment 2 as well. And then we can move on to the process of getting some live measurements. So we can pop all of this back together, get the power back on in a safe way. Obviously some of the exposed lighting has been disconnected for the time being, so there's no electrical energy going to those anyway. But there are other points in the circuits where we can do it. I will show you how I do it and why I do it, and the same with the sockets as well. But for the minute, this might just speed up a little bit while I'm just going to be prattling about on here, getting some measurements. It would take too long to show in the video itself, but I'm going to start this end of the board. If I get the right size screwdriver in, it would be a good start. So thankfully with this one, it's, like much of the rest of the install, been reasonably well dressed. So it's fairly obvious where all of the conductors are. I'm not going to have too much trouble identifying what's what. And I should be able to make a pretty easy and quick job of testing it in truth, which is nice. And then likewise, when it all goes back together, the intention is to put it back in a way that the same is possible for the next person. So this is just one of the ring circuits at the end here. We'll run through the process of your dead tests. Just give them a little straighten out. We can see very easily which leg is which. And again, with this, I'm going to be using the TIS MFT Pro, and it has a certain orientation of the leads within it. So if I pop it on, and again, I don't know how this is coming across on camera. I'll move you in a bit closer in a sec so you can have a look at some of the testing over here. But essentially, you're going to continuity, and it wants to use the black and the blue probes. So first things first on this, with the end-to-end resistance tests on the ring vinyl circuits, to make sure your leads are nulled. And the TIS is pretty good at that. It does it all itself and automatically. So you just hit the zeroing button, it runs through its little process, gives you a thumbs up to say it's happy, and then we know the leads aren't going to add any impedance to those values. And then it's just a case, quite simply, of getting your end-to-end measurements. So obviously we can start with R1, which is your little R1, and if we hit test, if this ring has continuity, it will give us a reading. I don't know if you can see that there, but it has done so. We've got 0.21 ohms, so we should find on the neutral, so this is your little RN, the same, roughly speaking. Obviously there'll be a slight variation because of the way the cables are dressed at some of the accessories. They could be longer or shorter, but there or thereabouts, and it's 0.23 ohms. So we're happy with that one. We can now pop it onto the CPC, And again, this should be a continuous ring. We'd expect this to be a little bit higher. Okay, now we've done the little R2 and I've got 0.35. Now the highest value I had there was 0.23. If you double that, it takes you up to 0.46. We know it's 1.67 times, so we need to be less than that. So there's a very quick calculation in your brain without getting your phone out to start punching numbers in. You can see that that's not far away. That probably plays out pretty well. And again, there will be some variation on that, the way the cables are dressed. You know, these are all a pretty similar length inside the consumer unit, but some of the sockets might have a different way the terminations are all connected together with longer and shorter lengths of your lines and your CPCs. So obviously you need to keep that in mind. It's not going to be an exact, 1.67 times, and your R1 and Rn is going to be the same. It's just not. So now we need to make our crossover tests. And the way you do that is essentially you take the leg of one of the ring, which is this one, with the leg of the other, and you make some crossover connections. So I need to go and get my little set of clips out now so I can do that, and then we can go off and take some measurements around at the socket fronts on this circuit, and primarily the values should be roughly the same, and that would be your big R1 plus your big R2, and you can also throw the neutral in there as well, so you can basically cross over your line and CPC on this leg with your line and CPC on the other leg, run around and get your R1, R2s, should be reasonably consistent aside for any spares that might be in the circuit. And then you can come back and basically cross over your line with your neutral and your line with your other neutral, and then go off and measure for resistance between line and neutral at all the sockets. And again, you should have a pretty consistent value as you move around that ring final circuit. So once you've done that, you can play with the maths a little bit. So if you take your little R1 and you add it to your little R2, you'll come to a value. If you then divide that by 4, you should roughly have the value of your big R1 plus big R2. So the crossover measurement between your line and CPC at every socket circuit. And I've shown that again on earlier videos on my channel at the office where we've sat and gone through the maths and broken that down. But that's roughly what you should see. And again, it's not a fine science. There will be some variation in it. It's just a rule of thumb to let you know you're sort of in the right ballpark. But I'll get the connectors set up and we'll zoom around and do all that. So you'll see there I put the little jumping leads across. They will add a little bit of impedance to the circuit. You can pop them into Eicrs if you want, but these have obviously got bent over ends and there's nothing wrong with them, so I'm not going to be redoing those just for the sake of adding some Eicrs. Yeah, so we can go off, get our R1, R2s now, all the socket circuits, and then I'll jump back, and as I said, I'll just replace that onto the neutrals, and then we'll have a little look maybe at doing an IR test on a lighting circuit or something. I'm trying to zoom through this as fast as possible. If I go through fully testing this board, this video is just going to end up too long. Okay, so I've got 0.18. It's actually a very small ring that just goes to this little utility room to the side of me there. Point of note when you're using this lead, on the TIS you need to be connected into the B1 and basically the line and neutral terminals, but you need to remember that you're measuring on the socket outlet between line and earth, so you need to put your line and your CPC into those terminals so you can take the reading. And that kind of plays out with the maths. I think roughly speaking, if you added little r1 to little r2, you were around 0.6. If you make that division by 4, you're sort of around 0.15. And then we said there's all the tolerances in these extra little bits of leads, the terminations through the socket front itself. They're all going to have a small impact, and that's a pretty acceptable value. So that's the big R1 plus big R2 on this very, very small little ring final circuit, which literally just jumps to my right hand side and goes around the utility room. Okay, so I've just repeated that process now for the R1 and Rn. It's not a test you need to record on the test sheets anywhere, but it is sometimes worth doing, and especially in this case when we've had water everywhere, it's a good way of verifying any of the terminations through the socket fronts, for example. This is a part of the building which supposedly hasn't seen any water ingress to anything, so it's well worth doing those checks if the accessories might not be getting swapped. So we've done that, and now we can look at the insulation resistance. So obviously I'm going to run through the dead tests on the rest of these socket circuits now, and the lighting circuits, and when I say dead tests I mean the continuity tests. With the lights, you can join your CPCs into your lines if you want, and this is the way I tend to do it, is take them out and pop them into a little Eicr, or use some crocodile clips, just so you're outside of any of the terminals within the consumer unit itself. Some people would take the CPC and just pop it into the top of the MCB with the line. Perfectly acceptable way of doing that, obviously, as long as the power's off. And then basically you find the end point of that radial circuit, so that's a radial, not a ring, and you go and take a measurement between the line and between the CPC, and that's the value of your big R1 plus big R2. And then again, you can repeat that process with the neutral as well. So you can cross over with the line and the neutral at the consumer unit, and then go off to the same point of that circuit and take another measurement. And that's just a way of verifying that all your circuit conductors have continuity from end to end. And then yeah, you're at the stage where you do an insulation resistance test. Now you can do the global IR, which in that case you basically dress all of the cables back into the consumer unit. You must make sure everything is connected when you're doing your IR testing. So obviously when you're doing your continuity testing, you don't want any of those parallel paths in place on the circuit, so you've got them disconnected from the earthing system. But when you're doing your insulation resistance testing, it's very important that all of those are in place, because you could be having a leak through some of the cabling into the bonding, for example, or some other part of the building that would find its way back to the consumer unit. So you must make sure everything is dressed away. And then you make a measurement between your, well, we'll show it, but I'm going to do this circuit by circuit. And the reason is we've got lighting equipment connected, so I'm not going to be able to do a measurement, for example, between line and neutral on the lighting circuit, but I will be on the socket circuit. So we can just run through and quickly do that with everything connected up. So yeah, when we're at that stage, I'll cut back to the video and we'll just do a quick IR test on the lights, for example, and then also on one of the socket circuits. And I can show you how the IR might plummet with the final accessories connected as well. I have demonstrated that on the test board at the unit as well. But yeah, we'll do that. I think it makes sense. So just give me a minute while I zip through this. Be a minute for you, be about an hour and a half for me, and then we'll pop back and do some IR testing. So with the sockets on the IR testing, well, I say it's the sockets, it's the cooker as well. Obviously we can do that with all of the loads disconnected. We're unplugged, got the cooker switch in the off position. We can then turn all of these MCBs on. Obviously the power's still off, this is a dead test. Put our crock clip up onto the earth bar, and you can test all of those in one go to the IR value between your line and your earth. And you do that just by going onto any one of these that you wish. And if you hit the test button, it'll start applying that voltage. And I am measuring clear of 500 megohms. So it's saying we don't have any issue between the line and the CPCs on those socket circuits. So it's quite happy with that. And again, you can repeat that process between the CPC and the neutral. So same principle. Obviously this is the neutral bar for these circuits. The RCD that feeds into that is in the off position. So there's no connection between the neutral bar for the lighting circuits. And again, it's giving a reading of over 499 megohms. And then equally, if you wish, you can then take a measurement between the line and neutral. Now with this one, you need to be careful if you have any equipment connected in circuit. This is where the readings will start to go a bit haywire. And again, I would always encourage starting at 250 volts before you go straight to the 500. Then again, you can take a measurement. And so yeah, again, between the neutral and the lines, we've got over 500 megohms. Now if I am to repeat that, for example, on this side where we know that there is lighting connected in circuit, and we'll keep it at 250 volts. And again, if I turn, doesn't really matter because the RCD is off, but we turn all these lighting MCBs into the on position, we can test all of those at once as well. Now this should be a very low number because I know there's equipment connected in the circuit, and it is, it's 0.02 megohms. So yeah, that's kind of what you would expect. And if you want to go to the trouble of disconnecting all of the light fittings, the immersion elements that might be on there or whatever else, then you can do. If you've got local isolators, it makes it a little bit easier, so you can just test up to that point of isolation for the connected equipment. But let's be honest, if you've got a house full of spotlights, you're going to cause more damage and destruction going around doing that, interfering with the installation, than adjusting the way you carry out your testing. And in that case, it is a simple, you simply join between the neutral and the line, and then you take a measurement to your earth. And I'll get that set up and show you how I go about achieving that. Okay, so now I've essentially joined the line and the neutral together on this group of circuits. So this is where your safe isolation comes in, and I've shown that earlier on in this video. You must be absolutely certain that there is no possibility of you accidentally switching this main switch back on while you're doing this, because it would be very, very unpleasant right in front of your face at this kind of height. And that is where having a lock off away from the board you're working on is absolutely brilliant, and that's what I've got here. Now if we look through this, you can see what I've done. So the MCBs are in the on position. I've got the little crocodile clip on the bus bar down here, and it is just for those circuits. This is a split load board, and I've attached that onto the neutral terminal bar for those final circuits as well. So I've essentially joined the lines and the neutrals together very quickly and simply without interfering with any of these terminations, which is great. And then I've got the crocodile clip up onto the earth bar up there, and if I use my little probe now, I could go onto this neutral bar here to take the measurement, or into the little cage terminal on the lines, or onto the bus bar. Anywhere I want on there gives me a connection to take the measurement. So I'm just going to very easily stick it on these top screws up here, hit the button, and there we go. So we have that measurement, and it's fine, it's clear. So it's measuring 210 megohms. So it's not reading off the scale, but it's plenty high enough. And that is probably due to the moisture ingress into the final accessories that I was worried about. So while the building's been dried out, obviously those terminals will have some sort of tracking through them. So at the very least, we're going to have all of these circuit accessories changed. And when that process is completed, those values should rise back up. I can verify that on one or two of the circuits, which I will do now. So I'll go and take some of the accessories off. I can do that quite easily actually on the upstairs lighting circuit, and we'll see if the cabling itself is clear. It could be that some of the moisture's tracked back down that cabling, we've had a breakdown of the insulation. If that turns out to be the case, you know, whilst it's reading at an acceptable value, I would be very unwilling to return that to long-term service, having had all the plasterboard stripped off and all of the new kitchens fitted and other bits and pieces, for the sake of pulling in some new cable to get those values back up to good as new. I think it's a bit foolish. So that's kind of the way I'm going to be approaching this one. You know, you've got those minimum set values within the regulations to use as guidance, and if you were wanting to just make a simple addition to a circuit, obviously you would know that that circuit was acceptable to do so. But I think in this situation, where you could have a potential for that problem to worsen because you know there has been moisture ingress, you wouldn't want to be in the position of having had the whole building put back together and then need to be taken apart again, because that problem's then got worse. So that's kind of where I'm at with that. I'm going to do a bit more investigation on that one. I'll zoom the video across now with me, and we can get to the stage where we've got the power back on. Obviously there's some of the RCD testing. We'll maybe have a look at that as well actually, because RCD testing is always an interesting one. And we'll get some live ZS measurements off a socket and off a light fitting, something like that. So I'll see you in a little while. Okay, so this is the socket circuit on that utility ring final that I tested earlier on in this video, and you'll see it's given us an earth fault loop impedance value of 0.29 ohms. Now that is a little bit under what the calculation tells us it should be. I think it was 0.18 on the R1, R2 for this circuit, and then we had around the same again for our ZE. So, you know, we should be around 0.36, 37, something like that, and we're obviously underneath it. You know, that's because we've got the bonds in place. This is a true impedance path of this circuit that's been carried out under live conditions, so we know we have an accurate value. It's not based on some calculations. This is an actual recorded measurement. And if we use the calculation method, it gives us a different figure to this. It would still be acceptable to use it because it would be erring on the side of caution in this example, so we're measuring underneath that value. But as I've explained on other videos, it doesn't always pan out like that. It can, in some cases, be reading lower than the true impedance path, and that can be due to a high resistance point through an MCB, for example. There was a big garage fire earlier on in my YouTube video YouTube videos that showed exactly that, and that was due to a high impedance MCB. But we'll move on and we'll get some ZS measurements at a light fitting. Okay, so I've got all this set up while the electrical energy was disconnected, so MCB switched off. We've crop clipped onto the earth, then gone and restored the power with the bayonet lamp holder in and my little probe into there as well. So I'm well away from anything that can cause me anything like danger. I've got the TIS test set up. You can see we're measuring voltage, so I'm at a very safe distance. And again, I can carry out these tests now and get a recorded value. And you can see I've got 1.24 ohms and 140 amps as my prospective fault current, if you like, at this point in the circuit. Now that is considerably higher than the dead test measurements I was getting, and there's a good reason for that, and we'll explain why in a little minute. But if we look up there now, I can now go off and disconnect the MCB again, open it, remove all of these connections and put it back together, and then do my functional check to make sure that the lamp actually illuminates. So that's the air fault loop impedance done on the lighting circuit. Again, very, very safe. I've had no access to any of the light terminals while I've been attaching probes. They've been dead. And then when I've carried out the measurement, I'm at a safe distance. I'm not near any of the bitey stuff. And that value has provided us with some insight into the condition of the electrical installation. We've got high impedance that's been measured through the MCB, otherwise would be unknown. In this case, it's not going to actually cause a problem as yet, but we do know that there's a component now connected in the electrical system that is maybe not in the best health. And again, on this particular job, having knowledge of the excess water that's been flowing around the place, carrying out your air fault loop impedance testing can provide some real insight that dead tests might not otherwise pick up. You know, your high resistance joints are all well and good, but when you've got moisture tracking about the place, you know, they can be, as we know, they can present themselves more obviously under energized conditions, but it's well worth ensuring you are safe while you do it. I totally get that. I've had people chuck accusations at me that I am hell-bent on testing everything live and sharing reckless and unsafe working methods. It's just not the case. I'm trying to ensure that my clients and customers receive detailed and accurate reports that represent the safety of their electrical systems, whilst also keeping myself safe while I do it. There is no reason that you cannot carry out air fault loop impedance tests and be safe. It's like one excludes the other. It's just not true. It's a myth. And the myth also that it doesn't give any extra value in carrying out that test. Another myth. I've shown it 3 or 4 times on this channel. It gives you real insight into the condition of an electrical installation. And yeah, I recommend that you consider it. At least consider it. Don't just blindly be going around doing your R1, R2s and your ZEs, chucking the numbers together and entering them into a box on a test sheet, because it might not be the actual value that's present. I've shown you it, so just keep that in mind. I can now go and make sure we disconnect all of this. We're going to run through some RCD testing, which is much more interesting than ZS testing, and then I will a conclusion with you based on the measurements I've obtained, some of the observations I've made, and explain what's going to happen going forward. So you can see through all the time I've been messing about on this system, that's its maximum, and its minimum is down at 63. If I clear that off now, I'm sure there would be a way to do that, but I've just switched it off and on again because I'm a heathen. And you can see there it's sort of around 70, 75 at the minute. So yeah, it's just interesting to see what can actually be flowing through an earthing system. Obviously when you're inside the potential zone and everything is connected, it's not such an issue, but when you're disconnecting conductors to carry out test measurements, you need to be aware there could be different potentials in close proximity to yourself where you might come into danger, so be aware of it. For example, if you are disconnecting the main earthing conductor and you've still got all of your protective bonds and you put yourself between those 2 points, you can make yourself part of that circuit. So just be aware of it and keep yourself safe. So we can do some RCD testing now. You'll see I've got it all set up down there. We're all good to go in the auto mode. If I hit the test button, you'll see it starts to do its ramp, and we've got 22 milliseconds. That's one test in the 0 degree pane. Same again at 180. We'll just stay up here. You can see how quick and easy this is. So there we go. we have got our 0 and 180 degree tests on the RCD, and you can see we tripped out on the ramp at 22.5 milliamps, which is okay, that's nothing wrong with that. Times 1 at 19 and 9, and times 5 at 7 milliseconds, and it didn't trip at all on the half-time test. So that's a healthy RCD on that circuit. There is a bit of a fuss over RCD testing, and it can cause, if you go off and look at the Eicr channel, they had, I think it was Luden, Mega and the ECA on to talk about RCD testing. In terms of complying with regulations, you only need to test your RCDs as if they were a type AC. However, if you are aware that there could be some DC leakage affecting things within that circuit and you've got a type A RCD, you might also want to test it in the type A mode as well, but you're not obliged to do so. And obviously if you've got something where you know that's not a possibility, you know there's plenty of circuits out there which won't have DC leakage within them, then you don't need to be doing it. So there's no hard and fast rule, just a case of judge it yourself as you go along. And if you are wanting to follow the guidance within the regs, it's still perfectly acceptable to just test them as if they are type AC RCDs. But that may change in the future, who knows what's coming. Is what it is. It's only a very simple and quick test, you've just seen me do it there. It doesn't take especially long, so it's not a great hardship. However, if you imagine if this was a 3-phase 24-way board on a massive commercial install, and they all need their RCD tests to be done in varying different ways that result in more work, then the time frame for it being done can be increased, and it's a cost to your consumers. So you need to make sure that that cost is justified and it is a test that needs to be done. Otherwise you are charging them for something that's not needed. That's my long and short take on that. Yeah, so that's kind of where we're at now. We've gone through all of the course of the tests. We've done the dead live test, we've done the safe isolation, we've done all of the ZE and PFC, PSC. We've been around and done the observations on the installation, and the values that have been obtained, would lead me to believe that the original install was done to a very good standard. I'm not too unhappy with that. You can see the way the cables are run around the building. If I show you, for example, there's been a bit of care and attention put in to the way it's dressed about the place. So you know that there's been a bit of effort put into it, and that shows. So it's not too bad. In fact, it's good. And in terms of the water ingress, there's definitely been a lot of that within the electrical accessories. The wiring itself seems to be in reasonable order. Basically the sockets where I know there's been heavy water ingress in them, I can see the corrosion in the back of the socket fronts, for example. We're going to say that all of the cabling down to those should be changed. Equally, all of the circuit accessories should be changed. The light fittings the same, they've all been flooded, they want changing, and rewiring on the downstairs lighting circuits which have suffered from that water ingress. So yeah, there's work to be done now, but at least we know as a baseline that the parts of the install we suspected didn't have any water anywhere near it are all good to go. They've tested out just fine, there's no reason to start messing about with any of that. And equally the same upstairs, where plenty of the electrical equipment didn't suffer any water ingress, perfectly fine and serviceable and safe. And most of the loop in and loop out cable in between the light fittings, for example, is fine. It's just some of the switch drops that I'm going to say need to be changed. And yeah, it's one of those, when you are the inspector, obviously if this had been under flood water from a river, there's all sorts of sediment and stuff that can get into the electrical system. If you're in that sort of position and it's gone through the whole thing, you're at the kind of stage where a rewiring full is going to be essential for any of the socket circuits, for example, that have had that moisture getting into them. When you've had a flood, it's a little bit different. It's going to a leak. It's going to the effort of trying to find where the water has actually found its way, because obviously water is a searching fluid and it tends to always work its way into the electrical system in most places. So, detailed testing, make sure you're happy you know where it's been, any of the damage it could have caused, and that when you're putting stuff back into service, it's not suffered the effects of any water and moisture getting into it. Because obviously it's been used in a way that's beyond the external influences for that product. socket fronts and light switches that are used inside are not designed to be flooded with moisture. So as soon as they have been, and they've been used in a way that's beyond the manufacturer's instructions for that product, the simple fact that it's now dried out and works, does that mean it should be returned to normal service and be used again? I don't think so. I think that they should just be changed regardless, because you don't know if there's an inherent fault in there that might present several weeks or months later, beyond just the safety aspect of things. And that's what's going to be going into my report on this one. We're not doing any of the remedial or repair works on this, so I'm not trying to generate work for myself. It's other contractors who come in and take care of all of that. We're just here to give the expert opinion after the fact of fires and floods and such. So yeah, that's sort of where we're at on that one. We can wrap it up, I guess. I hope you found this mildly insightful and entertaining. I didn't go through the whole range of tests on the board. I've been here all day, and to just run through the recording and do the work on my own would have taken me forever and made this an incredibly long video. It's probably long enough already. If you have any questions or comments and you want to go back and see some other testing, look back to some of the videos earlier on in my channel. I think I've got a testing playlist actually, and you'll find plenty in there. I've covered pretty much all of the testing along the way so far. But yeah, get involved. I love the discussion that goes on in the comments on my videos. If you have anything you want to ask, any feedback you want to offer, any suggestions, any questions, fire away, and I will catch you all in the next one. Thank you very much for watching.